Hello, everybody. Welcome to the next seminar on function spaces. And our next speaker is A.Kh.Balci from Bielefeld, and she will talk about Sobolev-Orlicz spaces of differential forms. And so the floor is yours.
Thank you very much. So for the introduction, very nice invitation to this seminar, which I also try usually to follow, the Prague seminar of functional spaces. So thank you very much. Well, I will speak today about generalized versions of Sobolev-Orlicz spaces of differential forms. And this is the work still in progress with Mikhail Surnachev, which was started quite long ago already now, and hope to finish it soon. And well, I will speak about differential forms at the second part of my talk, but I will start with some introduction without differential forms. So this will be classical spaces of classical functional spaces. And I will speak mostly about two topics. This will be a density of smooth functions and the examples on Lavrentiev gap for Sobolev-Orlicz spaces. I don't know why I cannot. Okay, so this is the introduction in the sense. What I will consider during this talk. So this will be the first the integral functionals of this form. So this is the classical problem. Here I have the integrand big phi, which depends on the space variable and on the gradient of the function w. And we want to minimize this functional. So we want that, that this goes to minimum. Yes, so to minimize it. And the natural question, which appeared, you see, quite a while ago, in more than 100 years ago, is the question: what is the correct energy space here? And first people, they even didn't know what Sobolev space is. They thought about spaces of smooth functions as a natural space. And then they realized that the energy space is actually not the space of smooth functions, but some space of absolutely continuous on the line functions. And well, in the modern language, so the question is what is the space to minimize, and more precisely, if the, let's say, infimum taken over all functions from the energy space is equal to the infimum taken over all smooth functions. And here, of course, one need to think if also as well if this minimum is attained or not. So for the problems I will consider, I can take here minimum and minimum. So I will have the solutions. So it turns out that this inequality could happen. So the infimum taken over all functions could be smaller than infimum taken over smooth functions. And those examples are quite many in one-dimensional case, and the most popular in the literature is the example due to Mania. So he constructed the precise example in one dimension. Yes, so this is the integrand here. And this is actually the big of what I notation here is big phi. So this probably I need to write as well, big phi. Okay, so this, of course, in one dimension, this will be a simpler derivative, and this is how this functional looks like. So with a fixed boundary of values 0 at 0 and 1 and 1, one can actually calculate the minimum, which is x to the power 1 divided by 3. And one can see that this function is not a Lipschitz function, but it minimizes this integral function, so it belongs in somehow to the energy space. So this example, now let's turn to the functional spaces. So this question has some similarities to the question of density of smooth functions. So maybe I can skip this slide and this audience. So this is the classical result saying that smooth functions are dense in the classical Sobolev spaces. This is for all domains, and kind of a global result is due to Myers and Serin. But local result was known even before this paper. And well, the main tool, which we usually teach the students, yes, that one can actually use the modification with a convolution with the standard modifiers phi epsilon or Friedrichs modifiers to conclude that smooth functions are dense in the classical Sobolev space. So from the point of view of the previous slide, this will mean that if I do not have a dependence on the x in the integrand depends only on the gradient of the function, then there is no Lavrentiev gap. Now, well, if we consider some generalization of the classical spaces, in particular, we take not W1P, but we take here some arbitrary function, big phi, which is equipped with non-standard growth conditions, which means here that the estimate from above and from below is satisfied with the different powers P minus and P plus. Then in principle, it is possible that H is not W. And here are some standard definitions, which I will also not spend too much time on it. So one can define the Orlicz space equipped with a Luxemburg norm. And then in the usual way, one can define the Sobolev spaces and the norm in the space. And as a closure of smooth functions, one define the space H. So, okay, so here the spirit of the slide is in the title. So in principle, it could happen here that H is not W. And well, I will also speak about this these examples, let's say later for the differential forms. And now the next slide, I want to give you a short overview, of course not complete, of what one can study from the point of view of function spaces, or go into the level of PD, the regularity of solutions, and so on. So of course, the most number of the positive results are in the case when H is W, and here the number of application is very big, so one can study different things, so regularity of the solutions, and the boundedness of integral operators, Calderon-Zygmunt estimates. One can study problems of obstacles, go into the levels of manifolds, studied some even more general things like generalized Sobolev-Orlicz spaces. And well, recently, I think maybe 2 or 3 years ago, it was a nice book by Hergiletto and Hester, where they combined and considered many different models of this type and overview. And well, this case when H is not W, actually one can also study some applications. There are not so many. In particular, you will then have different notions of harmonic functions, which one will correspond to the minimization with respect to H, and the other with respect to W. And those could be done separately, was done, for example, by Zhikov, Alkhutov, and Surnachev. Okay, so let me briefly explain. So I think many people already seen this next several slides. So this is the first example of Lavrentiev gap in 2D. This example is due to Zhikov, and this is the famous model which many of you are here are experts and working with it. So this is the variable exponent. So one consider the integral function to be minimized as the gradient of W to some variable power P of X. And one can actually construct quite a simple example to show that here the Lavrentiev gap can take place. This is the example as the following. So here the variable exponent is piecewise constant function. And the omega is here, this is the omega. So this is the unit square into d. And the variable exponent takes two values. So it jumps from 2 plus epsilon in the vertical cone, so here, to 2 minus epsilon in the horizontal cone. And so the idea behind this example is to construct the function which will be in the energy space, but which is not smooth function. And this is this function. So this function has a jump in the origin, so it goes from -1/2 to 1/2. Here to 0 in this region. And this red lines here denotes a transition between 0 and 1/2 and 0 in -1/2 in the lower half plane. And so the simple explanation of this fact that this function does not belong, that this function from one point of view, it belongs to the energy space, but it's not smooth. And the second thing that you can think about that all the game is played around the crossing the dimension. So here 2 is the dimension of the space. And we know that if the index is bigger than dimension, yes, then we have classical embeddings of Sobolev function to the space of C0 alpha. From the other point of view, in the horizontal cone, we only are in the sense of some Lebesgue space, but we do not have embeddings to the C0 alpha. And from this point of view, this function u constructed here, if I now here combine these two pictures, I see that this jump in the origin is seen from one cone, but does not seen from the other cone. Okay, so then one can take a different model. One can take double phase potential, also celebrated model. So here one doesn't have any variable exponent, but we have here the transition between P and Q. And this, the example of Lavrentev gap, the first one was also due to Zhikov. Then this model was also studied firstly by Marcellini, and then the generalized example of Lavrentev gap for any dimension for one saddle point was constructed by Esposito, Leonetti, and Mingioni. And here the weight, now it jumps from 0 in this region to x2 to the power alpha in the vertical cone. And actually the function u is constructed in the same way. And so here also the dimension appears. In particular, you see here that there is a gap if P is smaller than D plus alpha, where alpha is the regularity of the weight, and this is smaller than Q, then there is a lack of higher regularity of the solution. Well, you saw that in both cases it was some dimensional threshold, in the sense that it was important that P or in the variable exponent or weight here, something should cross the dimension. And recently we constructed some general procedure, which first of all is, we can construct the examples for different models. We just have some algorithm we need, which we need some properties to check. Then we can construct the examples of Lavrentev gap, and we do not have this dependency on the dimension. And this was our result with the Dinin and Sunachev. So this is this algorithm, and this is our result. So what we have, okay, so I write here that D is equal to, but actually we have, we can do it in any dimension. So using some fractal barrier set instead of 1 point, we can construct the pair of the functions u and v with the following properties. So first of all, the gradient of u belong to L phi, and the gradient grad perp of phi belong to L phi star. Then we have the following properties. So first of all, the this product is 0 for smooth functions, but it is not 0 for the functions from W. And we can show that there is no density in this case, both for the spaces H and W and also for H0 and W0. And we have the Lavrentiev gap. So we do not have here any dimension restrictions. And also we can go to the high dimensions, but then we need to change the language here of not dealing with the great perp, but dealing with the divergence of some skew symmetric metrics. So this is the idea. So actually the idea here is that the contact set in this one saddle point example has the dimension 0, so this is 1 point. And we have the embedding. We have an embedding in one case, but in the case of P plus, but not in the case of P minus. This I explained already. And so to get rid of this dimensional restriction, which was always the case for the one saddle point, we increase the dimension of S using a counter barrier set. So this is the classical counter set, everybody knows it. So we always remove 1/3 of the interval, and the remaining part is also 1/3 and the other 1/3. So the Hausdorff dimension of this set is calculated here. So we need to divide logarithm of 2, so the remaining part is logarithm of 3. And this is some number, 0.631. This is not so important. The important thing is that 2 is the number of pieces which remains is this 3 to the power d. And in the sense, you will see that we will have now, instead of the dimension of the space, the dimension of the fractal barrier, Hausdorff dimension of this fractal set. And so here I showed just to get a feeling what it is. So this is for the variable exponent model, how the function u looks like and how the variable exponent looks like. So this fractal is called contour necklace. And you see here that the function is constructed similarly, but we kind of distribute this checkerboard structure to the contour barrier, and the function still jumps from -1/2 to 1/2, but using this contour barrier. And here, well, I think maybe not so much time. So this is the idea how we calculate the integrability of the gradient of u. And the idea here is that we need, first of all, we have these blocks. So to calculate the integrability, we need to scale them, to add them all. So how many do we have? And then to multiply it with the integral over one, over, let's say, one block. And doing this thing, we obtain this number here. And we know that to have this series converge, we need that this exponent should here satisfy this condition. So what do we see? We see that this fractional dimension d, this in the sense is any number between 0 and 1. So for the case p smaller d, then we have all the cases, yes, we do not have any dimensional restrictions. And this is the other function. This is not so clear right now for what do we need it, but actually we need the second function to construct a so-called separating function. And this is how this function looks like. So this function is constructed as a counter function on the layers. Okay, so this is not so important right now. Well, from this one, we will get then later that p plus is bigger than 2 minus d. And you see that both p minus and p plus now will be smaller than 2, smaller than dimension. So this is the spirit. And this is how to get them both to be bigger than 2. Then we need to use different functions, u and v. And those are the pictures. So in the sense, they change the roles. So the function u now becomes the function v from the previous construction, and vice versa. Well, so now I will go closer to the topic. So we want to go to the high dimensions, first of all, and we want to go to some more general structure, to the differential forms. So let me present what will be the building blocks in 3D. So if you now, we can see the not the square, but 3-dimensional cube. Then we will have 3 variables, and the first 2 variables we denote by x bar, and the last one by x3. And here this one building block, which was, you remember in 2D, this was this function, yes, which was from -1/2 to 1/2. And in 3D, this will have different structure in the sense. So this should be now some smooth version of the signum of this last variable. Well, so in the sense, this is similar, yes. And V0 will be constructed as you see here. So this is the formulas are not so important. The important thing is that the structure change in the sense. So first of all, V0 is nowhere constant anymore. And this object, then we realize that it exists and it is well known. This is called the Rankine vortex. This object we obtain. So then you see what we have here. We have that, let's say, now U0 is some function, and then in the high dimensions, we will always have that either U or V, one of them will be function, and the other will be, let's say, vector field, or yes, divergence of some skew-symmetric matrix, and so on. And we want now to see what happens if they are both the subjects U and V. They will be differential forms. So in the sense, no one of them should be any more function, but they could all be some differential forms. And since I want also to go now to some high dimensions, I want to show you just these 3 pictures. So this is how these fractals now for the U looks in 3D. This is much more complicated to draw them, but you can see that the fractals which we use can be, for example, constructed as some counter dust. So here, this is the first generation. So here you see this is the plane, yes, and so you also need to then to make the symmetric picture in the lower part of this plane. This will be too heavy, yes, to understand. So in the first step, we remove this squares, yes. Then so this is the second generation. Then on each of this remaining squares, we again remove these squares, and here, and so on. Yes, so then on the plane, the remaining singular set will be a counter dust then for 3 dimensions. And so this is about U. So to construct the second function, which was called V before, is to imagine how it looks like is even more complicated, but well, so you can see that this is possible in principle. Okay, so then let's go next to the differential forms. So I wrote here some naive definition. I will use the precise definition with exterior algebra and so on. I will also show you, but just in case that somebody is not so familiar with differential forms, this is in principle some naively speaking, this is some generalization of the notion of object f of x dx and of general of the notion of integration over some oriented curl or oriented surface or oriented manifold if we go to more general situation. And here there will be two parameters which will be important. So first will be this classical parameter, the dimension of the space. So now I'm sometimes this could be confusing. So n or d is the dimension of the space, yes. And the second important thing will be the dimension of the manifold or of the surface over which we will integrate in the sense, or in the other words, this is the order of the differential form. And so just some examples. So in the if this formally k is equals 1, we are in the spirit of my first part of my talk. So this will be about the functions. If k is equal 1, then one needs to let's say speak about formally about some vector fields or integration over oriented curl. And if we go then k equal 2, this could be considered as the result of integration over some oriented 2D surface and so on. This is the one way to look naively to this notion as an oriented density that can be integrated of some manifold in general. And here the important thing, even if you have a look to this very simple example, that it is important the direction, yes, so that we integrate from A to B, and if we integrate from B to A, we need to change the sign. And these questions of orientation are very important in this topic. Okay, so there are some operations which can be also defined formally using exterior algebra, but here just two things. So for the scalar function, everybody knows that one can actually multiply functions, and you get some properties which you usually have, and you can always, one can obtain some kind of derivative, yes, differential of the function which satisfy the product rule. And for the differential forms, there are some also basic things like this wedge project, which plays the role of product usual, and the exterior derivative, which is also called D, which in some sense could substitute taking the differential for the scalar functions. But here the rules are different because of this antisymmetric structure in the sense of all the stuff which is behind. And so there are some basic properties like that this operator, if we take D of D, it is 0. So what you can think about is that if you have a differential form, and if you have k equals 0, then you can think about taking a gradient, and for the k equal 1, about taking the rotation or curl, for the k equal 2, about the divergence. And this is what is usually used, let's say, more often, this operators. Okay, so here are the definitions of the formal definitions using exterior forms. So well, the spirit here is that you remember that the sign was very important, and then one can actually formally define these objects, which I defined naively at the previous slide. Yes, and this is the a formal definition of the wedge product or exterior product. which, as I said before, satisfy this standard usual properties. And they also, one can define this interior product. This is a little bit now, I'm using the notation from one book, which I will cite later. And this is this strange symbol, so for the interior product. So sometimes in the literature you can see this. So this is defined using the Hodge dual operator, taking the Hodge dual operator of the wedged product. And here is the definition of the Hodge dual operator. So in the sense, this is one of the main tool or one of the main operator which will be used. So this is actually saying that so you can define it actually differently, but this property which is written here, so this define completely this operator. So in the sense, this you see this connects the product, the usual scalar product with this wedge product. Okay, so this is the formal now definition of differential form and of the exterior derivative of differential form. But going now to the level of Sobolev-Orlicz spaces, we of course will use a weak derivative as we do it usually. So here is the definition of a weak derivative. So the definition of weak derivative for differential form is, you can see from this definition that it is quite standard, and this is as we usually define a weak derivative for the normal objects. So the important also fact, which is kind of also in principle can be used as a definition of differential form, is this Stokes-Cartan theorem, which I wrote here. So in particular for the functions, so if you consider functions or vector fields, this will be the classical Stokes theorem or divergence theorem for the vector fields. And this say that taking actually the exterior derivative of differential form is the same as taking the boundary of the domain. So you see in the sense this operation via versa, yes, we can either take the exterior derivative of the form, but then we will obtain the boundary of the domain. So this is the most general formulation which I will use here of this Stokes-Cartan theorem. And okay, so then let's go back to the exterior derivative. So if we now formally take the adjoint of exterior derivative, we end up with a very important operator as well. This is a Hodge codifferential. So this is defined as following. And now when I will speak about functional spaces, you see that here we need kind of to distinguish between differential and codifferential, because now we will have two objects which serve to make partial integration in the sense. So all the spaces will be either with respect to the differential now or to the codifferential. Okay, so now let's go back to the variational problem, but now with differential form. So this is now the functional. The functional now involve some object phi. This will be differential form, which depends on the x and the omega, and we want to minimize this functional. So here we need to have a function phi to be a Caretard-Dore function with the same non-standard growth conditions which I had before, and later for my examples I also will need that this generalized Orlicz functions satisfy delta 2 and nabla 2 conditions, but this will be later. And here omega is a k-1 differential form. So speaking general about variational problems of differential forms, there are some properties, or even I can take, you can say some difficulties which do not exist in the scalar case. So for example, this gauge freedom or gauge fixing. So what does it mean? So here, this is a bit maybe difficult to explain where it comes from, but you can think about this now. The system has too much degrees of freedom in the sense. So one cannot really find a solution or even saying about existence of the solution without additionally fixing either differential or subdifferential to be zero or to be prescribed. So you can think now about if you have a usual case, you sometimes need to have the conditions like divergence equals 0, for example, and without it you cannot do anything. And here the situation is the same. So the existence theorem I will state and the proof will always require this so-called gauge fixing. Okay, so for this problem, I want to study whenever we have also kind of the Lavrentiev gap or different minimum taken over all omega or smooth omega, and the non-density of smooth functions. Yes, in this generalized Sobolev-Orlicz spaces. And now you see that I have here the symbol D. And this symbol D will now means that I'm speaking about so-called partial spaces. That means that the spaces, they involve differential, but this formal definition I will give later. Okay, so what about general things which are known till now on calculus of variations, the spaces of differential forms? So this topic is quite classical in the sense, but things about kind of regularity or density or even functional spaces, this I would say is not so old, yes, as the differential forms in principle, which go back to maybe 50s, 40s, and so on. So classical regularity theory, so in particular this gauge fixing and so on, this is due to Uhlenbeck, and then there is also a classical paper by Hamburger involving the Hodge duality tricks, for example, from 80s. Then there is the kind of fundamental paper. This is a very long paper, around I think 75 or 80 pages, by Ivanich, Scott, and Strofolini, where they construct really the classical theory of Sobolev spaces of differential forms and nonlinear Hodge theory. So all the classical spaces like W1, P, omega, and the K, density of smooth functions, different properties of these functional spaces. So all this contains in this article. So more recent developments of Hodge theory are contained in the very nice book by Xato, Dakaroglu, and Noyes, which is called Pullback Equations of Differential Forms, and which we used as a basic book to study. Then going to the level of equations, let's say of Euler-Lagrange equation for these problems, one can study regularity of the solution, and here there is not so much known. So there is some partial regularity results for the differential forms, and this is contains in the paper by Beck and Strofolini. And recently there were several papers and PhD thesis of Seal, where he studied kind of nonlinear Stein theorem and also constructed, let's say, more in his PhD thesis, more general theory involving existence of minimizers, and even maybe I didn't mention it, so I always consider only the convex case for the integrand. So he also has some kind of quasi-convex, so on, very very general, nice papers and theses. And what we will do, we will consider generalized Sobolev-Orlicz spaces of differential forms and obtain density results and construct examples of Lavrentiev gap. Okay, so I think I'm a little bit over of time, but I will try not to not to be very fast. So I think in this nice seminar, I can just skip this slide. This is about definition of Lebesgue spaces and space smooth functions. They are defined as usual. And here, the only difference, so Sobolev-Orlicz space is defined as usual. The norms is defined component-wise, and here the difference from the classical spaces will be that in this case, you see we have different spaces. So we have the spaces which are contain the measuring of the only differential, and here only of a co-differential. And one can also work with the so-called total Sobolev spaces, but this I will not do. So first of all, those spaces has a good properties. They are Banach spaces, so we can work with them. The next thing we will need is some notion of trace spaces, and for this one need to take a decomposition of the boundary into its tangential and normal components. And what is the spirit that one actually decompose here omega to its tangential normal component. So here also we will use it later. And those are definitions now of the tangential space and normal space, which here I will use only one of them. Some definition which actually involves here this two different formulas, one with the d omega and one with the delta omega. This I will probably also skip. So there are some integration by part formulas. Well, put it like this: one can integrate by parts. Yes, so not as simple as it is in the usual case, but one can do this. Let me now formulate and shortly show you the proof of the existence of minimizer. So if we have a bounded smooth set, and we have some generalized Orlicz function with a delta 2 and nabla 2 conditions, growth conditions, then our variational problem has a solution in this partial space equipped with a tangent, yes, this tangential part, and sigma here means that I need the condition sigma is 0, the additional fixing. Okay, so we prove it actually. The main component, I will say, we use in the proof contained in the thesis of C, where he considered the question of existence in the usual Sobolev spaces. So he proved that actually we can find some let's say alpha S, which belongs to the classical space, to the space with a fixed here exponent. So this is the lower index, and using this kind of what we call, put it like this, direct method of calculus of variations. Yes, and then we can do this for this equation as well. Okay, so this is our first result. So density of smooth functions. We can prove some generalization of the result of Zhikov, which was for the scalar case. Here we have the following. So if we are given this integrand phi, then we can construct we can construct the phi epsilon. There exists phi epsilon such that they are convex and measurable, such that this properties holds. So sorry, is it some question because I cannot see anybody. That's why. So if this properties holds, then there is density. Okay. Then let's move further. So this is when we have density. Now, how we construct the examples of Lavrentiev gap, actually the framework is the same as for the scalar case, but here, let's say everything becomes more difficult. In particular, here, the functions, these basic functions u and a, are defined using the fundamental solution to Laplace equation with the polar origin. So this is the formula. And this is the definition here of the functions of u and a. And here I write this norms in this infinity norms. This is just for simplicity. Actually, one can take other norm. This is not so important. Okay, so we defined in the sense this building forms, and here, okay, so this is now how this parts from the previous slide are defined, and we use also the function theta, which is a smooth increasing function, which is plotted here in this small picture. Okay, and so our basic forms have the good properties, and the good properties here for me means that first of all, if we multiply them, then almost everywhere the product of du and dA is 0 in omega. And the second is that the boundary integrals here are not 0. This is important. Well, so here it was a bit tricky, because you remember all the examples I considered in the first part of my talk were living on the cube or in the on the square. And then so it was quite surprising for us that most of the results we found in the literature for the fractional forms are only for the kind of for the smooth boundaries and so on. But here it's not a problem, because since this forms, I mean, if I take d of this product that is 0, then the same holds for the boundary of any ball. So we can, in the sense, put everything inside some ball. And we also have a good integrability properties of du and dA. So in particular, the main here is that the coefficients of the forms both belong to the usual Sobolev space, W11. And here we have a good integrability estimates, let's say, for both of them. Then we have also to construct new singular sets. So in particular, in opposite to the first part, here the control set we use are also more have the different structure. So I will explain what does it mean. So here again, this picture of 1/3 contour set, and here we will construct some contour set which will remove them in each level. We will remove the interval of the not constant length, but of the length which could be different. And this is very helpful for us, because it using this major contour sets, for example, which decrease exponentially, we can treat more examples, in particular some borderline cases, which I will show you later. So then we have some good estimates of this contour measures in the neighborhood of our singular sets. This is here. that everything in the neighborhood of this Boas has a good estimates. And also, yes, so here this the contour set by itself is denoted by the C, and this is the contour measure corresponding to this contour set. Okay, so here now are how now the functions U and A now are defined not for one singular point, but for the this contour barrier definitions. Okay, so now this du and dA defined for the fractals, they also have good properties. So they are summable, the product is 0, and these boundary integrals are non-zero. This is what we use to construct the examples of Lavrentiev gap. Okay, so now I will do some application, and the application I will do is the so-called borderline case of the double phase potential. So we were inspired by this paper of Baroni, Colombo, Mengione. So they considered in the sense borderline case. Well, I'm saying in the sense because the model we consider is different from there. So they considered with the one logarithmic factor here, and you see here the difference between let's say classical case and this double phase is only logarithmical. Yes, so this is the difference. So they have positive regularity results. So they have when U belongs to C0 beta phase vanishing, and so on. So they have some positive results. And first we considered for the scalar case this generalization of this model. So here we have the logarithmic factors with respect to both summands here. And for the case of one saddle point, we already proved density results and constructed examples of Lavrentiev gap in the previously, yes, also with Mikhail. So I will show you what we did. So here, this is the weight. Weight was here. This is weight. You see, this weight was jumping from 0 to 1. And this is this one saddle point. So this was already before, also by us, but in some previous project. So we here we have the full description of all the cases. So given the parameters alpha and beta, we can say when we have the Lavrentiev gap and when we have the density of smooth functions. And this is in this diagram. So given alpha and beta, we can say, okay, if alpha is beta bigger 1, then we have Lavrentiev gap. If alpha smaller 1, the saddle point is removable, so no Lavrentiev gap. And if alpha bigger 1 and beta from 0 to 1, then we can use the estimates for the modulus of continuity. Okay, so now this we had already, but for one saddle point. Now we will apply this differential form technique to the case of the fractal barrier to get not only P equals D, but all other cases. And here I just wrote the models which we can treat, so we can do all the functions of this form. So here this is not correct. This should be phi. Yes. So the integrand is bounded from above and from below by two Orlicz functions. And one of them so is controlled by the t to the p with this logarithmic factor, and the convex conjugate of psi is controlled by t to the p prime, this logarithmic factor. So in particular, this will include all these models like variable exponent, weighted p energy, double phase, and borderline case of double phase potential. So all this model we can treat. Yes, and here I just show how we check that all the properties of the form which we need are satisfied. are satisfied for this borderline case of the double phase potential. So here I wrote down the admissible range of parameters we got for the borderline case. So first of all, I want to say that we only can deal with the case alpha plus beta bigger P. And for here, for this case, we have the following. So if P is bigger than D divided by K, this is how the singular set is constructed. This is the dimension of singular set. And this is what is P. And then we have the range of parameters when P, and this case P bigger D divided by K, this corresponds to the scalar case P bigger D. And if P is smaller than D divided by K, we also have the singular set, the dimensional fractal set, and what is P. And the same we have for the case where P equal to D divided by K. And here, when the D is equal 0, you see, so for this, we need to use this modified, very thin major counter sets. And so then we can, then for gamma, and gamma here is this parameter from the counter set, there exists a non-trivial linear function which is actually 0 on smooth functions, and this is non-trivial on the functions from this partial space of differential forms. So this in particular shows that smooth functions are not dense in those spaces. And let me summarize because I'm already late, sorry for this. So we consider generalized Sobolev-Orlicz spaces of differential forms. We constructed examples on Lavrentiev gap. And especially what was new even for the scalar case, this was the description of the borderline case of double phase, for which we got the admissible range of parameters to construct the examples of Lavrentiev gap and non-density of smooth functions. And unfortunately, well, our method cannot catch the case alpha plus beta smaller p. So for this case, we really do not know. This now, if we compare it to the results, the positive results of Baroni, Colombo, Mengioni, this right now does not fit because their alpha plus beta could be a smaller p. So here we don't know. So our method right now does not work. But for all alpha plus beta bigger p, we have the full description. So thank you very much for your attention. This was all for today.
Yeah, so thank you very much, Anna, for this interesting talk. And so if there are any questions, then anybody in the audience is welcome to unmute themselves and ask their questions.
May I ask?
Yes, for sure.
Thank you very much. It was very interesting talk. I was wondering about your omega, because sometimes you told us that omega is a bounded smooth open set. But then you had a lemma where you had bounded star shaped with respect to a point. And those sets can be quite, you might have spikes and so on. So what about your main theorems? What do you assume about omega?
Well, so for the main theorems, the point is that we only consider everything on the cube. On the n-dimensional cube. So, but even here for the differential forms, it was not so obvious because we need to take this cube inside the bigger ball. And only in this case we can treat it. But we only have right now a very simple domain.
Okay, but anyway, that was very nice. Thank you. Thank you.
Thank you.
Okay. Yeah, thank you. Are there any other questions?
There's one in the chat line.
Ah, yeah. Yeah, so I can read the question in the chat. Yeah, have you tried convex integration to produce or reproduce examples of Lavrentiev?
Convex integration? No. No. I don't know convex integration, unfortunately. But yeah, it would be interesting.
Maybe some other questions. So let me ask just for curiosity. So what are your next plans in this topic?
Well, so this was a new topic for us, this differential forms. So we still study a lot. So the next question for us will be to combine our knowledge, let's say, what does this Lavrentiev gap means for some classical facts which they have for the differential forms, like they have some Gaffney's inequality, they have some special things which we want to understand in our language. Yes, so I think this is more like now, this is about understanding more, because this was kind of really quite difficult for us even to reformulate things in the new language. And there are also like many different counterexamples going like more in the direction of geometrical analysis, which could be also connected with the counterexamples on Lavrentiev gap, but we're still working on to realize if they're connected or not, or things like this. So
okay, yeah, so it seems that there is a lot left open to investigate. And so are there some other questions? Yeah, so if not, then let me thank Anna once again. And maybe Luboš can invite us for the next seminar.